and I will discuss the lecture 2 of a clinical chemistry. So in the first, because these are my notes, the first in the nasopharyngeal, because it's important that the Epstein-Barr virus, it contains DNA in the case of the nasopharyngeal carcinoma. Actually, the Epstein-Barr virus, it contains DNA, double standards of the DNA. Okay, so now we talk about, what are the lab errors that is can maybe happen, and this stuff, or we are just dealing with the lab. So the first one, we will discuss something like influencing factors, and there is something is called interfering factors. These are, we can say, it's a pre-analytic errors, or the factors that affecting the analysis. The first one, influencing the factors. These are the effects or the factors that affect the lab results from the biological origin. Mostly occur in vivo. And you know what is vivo? That's mean the organism itself. But also can derived from the sample in vitro. Vitro, that's mean outside the organism. Vivo, inside the organism. During the transport, the storage, and the other thing that's so important, it's independent of the applied analytic method. Whatever the analytic method that I use, it doesn't depend on it. So now we understand what is influencing factors. Influencing factors are the factors that is affect the lab results, mostly from the biological origin. Again, influencing factors that is affect the lab results from biological origins, and we can say that mostly occur in vivo. And I mean in vivo, inside the organism, but some that is going to occur from the sample, so we can say vitro, outside the organism. Is that depending on the analytic method? No, it doesn't depend on the analytic method. So we want to know what are the factors in vivo, the organism, that is affect, the analysis, especially the pre-analytic errors. So the first one is age, body position, physical activity, diet, disease, genetic factors. And the question is how? Because age, some what is the creatinine level, the other thing that in the old age, how is it, in the young age, how is it, in the fetus, how is it. So it will be changeable according to the age. Other thing, body position. Sometimes when you vertical, the concentration increase, the physical activity, if you are exercise or not. Diet, if that is the sample postprandial or preprandial, and that is affect the lipid in the sample. Disease, maybe this person has a disease, okay, or environmental factor or accidents, or that is maybe due to the genetic factors. So all these factors under the influencing factors, and we said that most in the vivo. So age, posterior, physical activity, disease, genetic factors, diet. And the question is, what or how different sampling technique affects the lab values. We can say it's a vitro factors, but they are under the influencing factors. We can say it's a sampling that is associated with a sampling technique, like maybe prolonged stasis, maybe pumping with the fist, maybe sample mixing, maybe cannula diameter. And just these are, we can say, influencing factors, but in vitro. That's mean outside the organism, it because of the sample itself. It's still that is not depending on the analytic method. Okay, so again, I will just describe how that this can be happen. So the first factor is a prolonged stasis. Okay, how that is a prolonged stasis? I mean the sampling technique itself. Because maybe just make a tourniquet, and should we, when we do this tourniquet for a specific time, but if it's applied for a prolonged time, then that is leaded to the prolonged stasis. And if we just expose it to the prolonged stasis, that is lead to an increase the bilirubin, the cholesterol, and potassium, and in the same time reduce the glucose, GGT, and also creatinine level. But we want to understand how that is can be happen. in a prolonged stasis. So the first one. So this is the first factor of influencing factors that is in the vitro. Okay, during the sampling technique. Why it's increased the bilirubin? Because stasis, that's mean damage of the RPCs. If this damage of the RPCs, then that is increasing the bilirubin. And I will discuss later how the damage of the RPCs lead to an increase the bilirubin. But keep in your mind, damage and the broken of the RPCs lead to the bilirubin, because we understand before that the hemolysis increasing the bilirubin, but we will discuss it in more details. The other thing, it increasing the cholesterol. Why? Because the RBCs is a cell, and the cell membrane composed of a lipid. Inside the intracellular matrix, most of them of the lipid. So when it's broken down, that is lead to an increase the cholesterol. And why is increasing the potassium level? Because the potassium, it will be inside the RBCs. This is the normal positions of the potassium, and then when it's a breakdown, then the potassium increase. So prolonged stasis, that is due to the prolonged tourniquet, that lead to an increase the bilirubin, the cholesterol, and the potassium level. Then we understand why the glucose level decrease, because it's consumptions of the cell to this glucose, so that is decrease the glucose level. And because this is affect the functions of the kidney and the functions of the liver, so that is decrease the amount of the creatinine and also the GGT. Now we talk about the pumping with the fist. Because of a pumping of the fist, that is leading this action or this, because you are just controlling the muscles, so that you pumping out of the potassium and the magnesium, so that is increasing the potassium and the magnesium. And then the cannula diameter, when it's a small cannula diameter, that is lead to the turbulence, and that is lead to the shear tear, and that is lead to the damage of the RBCs, makes hemolysis. And after hemolysis, it's mean increasing the potassium, bilirubin, and that is leading to the false elevated potassium or bilirubin. If we just measure the bilirubin in this sample, or measure the potassium in the sample, and by bad technique or by bad sampling technique, that is lead to false elevated bilirubin or potassium level. Then the sample mixing, how the sample mixing affecting that? Sample mixing, if it's over mixing, when you just make mixing but over mixing, then that causes medical force, and that is leading to shear stress, RBCs rupture, lead to the hemolysis, and you know what is happening. Bilirubin elevated, potassium elevated, cholesterol elevated, glucose down, GGT down, creatinine down. But maybe we not mixing it very well, it's not probably, and that is leading to the microclots, and that is leading to the platelet aggregate, and after platelet aggregate, that is leading to the clotting, and that's also lead to the false results of a clotting, like maybe we just measure the TTT or BTT or something like that, and then that is leading to the false measures. Here I draw something to make it easy. Like, I want just to remember, we just remember all the factors that is happening in the vivo: age, posture, diet, physical activity, disease, what else, genetic disorders, genetic factors. These are associated with its organism, but the questions, the factors or influencing factors, that is associated with the vitro, I mean the sampling techniques. How to remember it? Just we remember the pumping with the fist, and also cannula, because it's related to the hand, and what is related to the sample, like a mixing of the sample or prolonged stasis. I just prolong the stasis like this, but it actually we can just draw a tourniquet. So just to remember these influencing factor, remember it's called influencing factors because they are affect lab results during or because of a biological or from the biological origin. So I draw here a cannula. We can make like I don't know, I feel that is more easy. Like this is a cannula, because we can explain the diameter of the cannula when it's small, that is lead to the shear stress, and that is lead to the mechanical force destroy of the RBCs, bilirubin increase, and all the hemolysis that is can be happen. Pumping with the fist, that is increase the potassium level and also the magnesium level. And then I put here a sample and I said prolong the stasis, and we discuss it. Mixing, I said over mixing leading to the hemolysis. Not mixing properly, that is leading to the clotting, because that is enhance the platelet aggregations. So we just finish the influencing factors. Now we go to the interference factors. These are not the interference factors. Interference factors, they lipema, also hemolysis, we can say hemolysis, lipema, and icterus. We will discuss it later. What are the interference factors? Factors that is lead to the falsely increase or falsely decrease lab test for a defined analyte. Like we just measure a defined analyte, and after we measure it, maybe that is lead to the falsely positive or falsely negative, falsely increase or falsely decrease. So that is the definition of the interference factors. Factors that is lead to the false decrease or increase of a defined analyte. Differ with the respect to the attempt analyte and analytic method, because it depends on the analytic method here. So that is the difference between the interference factor and influencing factors. Influencing factors that doesn't depend on the analytic method, while the interference factors depending on the analytic method. Okay, so differs with respect to the intent analyte and analytic method. Alter the result of the sample constitute after the specimen have been collected. That means affect the constitutes itself. So that's so important. I hear just we can say these interference factors from they are coming from where. I mean, maybe exogenous molecules present already in the sample. Okay, or exogenous molecules that we add to the sample, or biological constituents of this sample. We want to understand these things. Okay, so so the other thing that we are talking about is these are not the interference factors, So the first one, exogenous molecules are present in the sample, like maybe this person just maybe drink molecules or drink drugs, that is maybe drink drugs or take a tablet or something. So these are exogenous molecules that is present already in the sample, like drugs, or exogenous molecules that we add to the sample, like anticoagulants, or we just additives to these samples, or we make intravenous infusions. The other thing is biological constituents of the sample. Maybe the acetoacetate interfere with the creatinine measurements by Java methods. That means we use Java methods. Okay, why we use Java method? To measure the creatinine, and there is acetoacetate in the sample, and that is acetoacetate interfere with the creatinine level by the Java method. So these maybe we can examples of the interference factors: exogenous molecules that is present on the sample, already in the samples, or exogenous molecules that we add into the samples, or biological constituents already that is present in the sample, like acetoacetate, which is interfere with the creatinine measurements by the Java methods. But actually, the interfering factors, the first one is hemolysis. Hemolysis is the disruptions of the RBC's membrane, like break down this membrane, okay? Release of the contents, which is composed of hemoglobin, ferric acid, everything that will be released. Why it's the blood red? Because the hemoglobin, when it's go to the bloodstream or serum after the centrifugation, that is lead to the red color. The other information that we wanted to know that the hemoglobin is the most abundant protein in the hemolysis. So when the hemolysis occur, what is the most abundant protein? Is hemoglobin. Hemoglobin. Globin, it's a protein. So the hemoglobin is the most abundant protein in the hemolysis. And the questions is not always hemolysis happened with the release of the hemoglobin. Maybe it happens the hemolysis, but there is no release of the hemoglobin outside. Why? Because maybe it's the first one incomplete lysis. Like, okay, break down the RBCs, but the hemoglobin doesn't go out. Or maybe happy cell damage, but there is no bursting. There is cell damage. The cell is completely not working, but there is no bursting. No bursting. That means the contents are not outside. Or a quick clearance, like they are go outside, but then the liver removed it so rapidly. Or the hemoglobin go out, but binding with the other things, so we cannot realize the hemoglobin, which is give it the red color. Or hemolysis happened already, but there is low concentrations of hemoglobin. Maybe the questions will be in another model. That's mean sometimes the hemolysis happen, but there is no increasing of hemoglobin, because we said that the hemoglobin is the most abundant protein in the case of the hemolysis, and we just said that this sample is there, it contains a severe of hemolysis. Despite all these things, there is no increased level of the hemoglobin, and the question is why. Why? Because it's maybe incomplete lysis, or the like that happened damage to the RBCs but without bursting, or hemoglobin already go but it's rapidly cleared by the liver, or hemoglobin bind to other organism, or low concentrations of hemolysis. And the other question, why can red coloration of the serum or plasma never accurately predict the concentrations of the RBCs? The same thing, okay? Because if the red coloration it's associated or because of hemoglobin, because hemoglobin contains ferric, and that makes it red, okay? So that is not to predict the concentrations of the RBCs. Because incomplete lysis, because the dilution effect, because the plasma maybe dilute the hemoglobin, or the other substance like bilirubin proteins and other substance make like a dilution for it. So the red coloration not represent how many RBCs that is present, because maybe it contains the other components like bilirubin and the protein, maybe incomplete lysis, or maybe dilution effect. Some facts that the hemolysis is the most common pre-analytic error. It's really is the most common pre-analytic error. Okay, and they are, they are just under the interfering factors. We can say that the interfering factors, they are like exogenous molecules present already in the samples, or exogenous molecules that is added to the sample, or we can say what else, I have forgotten the other thing, like something biological components that are already present in the sample that is maybe affected. But the other thing that is most important, that the most important pre-analytic error is hemolysis, and 60% that is because in vitro, that's mean unstable sampling, unstable techniques that is used in the sample. But 3% in the vivo, and we discussed the vivo, like age, posture, physical activity, diet, disease, genetic factors, all these things, okay? But most of them in vitro, because of the sampling, because of the sample collecting. Sometimes we can say because of a sample collection or a sample handling. Sample collection like diurnal variation, posture, time of collection, fasting status, tourniquet, order of withdrawal, insufficient volume, or the handling with it. Okay? Okay. Now we go to mechanism of hemolysis interference, like how the hemolysis act as the interference factor. So the first one is spectrometric interference. How that is happen? Spectrophotometric, we know that the spectrophotometric measure the light, okay? measure how this analyte absorbs the light. Okay, so that is measure the absorption of the light. But sometimes when a breaking down of the RBCs, then release of hemoglobin, and the hemoglobin interfere with the light, and then if it's interfere with the light, so we can measure the another analyte. Okay, so what we have to do, we have to dilute this solution. After we dilute it, then we can measure the other analyte or a specific analyte. So that is causes the spectrophotometric interference. What else? Release of a cell component into the serum plasma. How is it? Like when there is a breakdown of the RBCs, that is lead to release of the potassium level and other substances. Some example like bilirubin, so that is lead to the falsely determined. If I want just to measure the potassium level, and then there is a hemolysis, so that is leading to the false positive of the potassium level. So I can say not release of the cell component, I can say falsely positive or negative of the analyte due to the release of the cell components due to the hemolysis. Sample dilution. It may be contain a solution of hemolysis, but it may be in the same times because of hemolysis dilute the measure or the concentrations of the measured analyte. The other thing is chemical interference. For example, if we want to measure the calcium or hormones or whatever, okay, it's the same time increase the bilirubin, and maybe the bilirubin have the same wavelength of the others, so that it can be lead to the false decrease of other substances, or that is lead to the chemical interference. So when I talking about what is the mechanism or what are the mechanism of hemolysis interference, I mean how the hemolysis interfere with the results of the lab. That is can maybe happen due the spectrophotometric interference or spectrophotometric interference. I mean here when there is hemolysis, so that is the release of hemoglobin interfere with the light. How we find the solution, or how we solve it? By the dilution. So you remember the dilution. So this dilution is also another problem. The dilution, it can maybe by the hemolysis, the solution it will be diluted to measure a specific analyte. The other thing that is maybe lead to the falsely negative, falsely results of ions or analyte due to the release of some components of the RBCs, and we can say the potassium level. The other thing is the chemical interference, like we want to measure the calcium or hormone or specific things, and it has the same wavelength as bilirubin, which is the results of hemolysis, and that is leading to the false negative or false positive of this specific analyte that I measure it. So these are the mechanism of hemolytic interference, and again the hemolysis is the most common pre-analytic errors, because we discussed now the pre-analytic errors. Okay, the second one is lipemia. Lipemia, that's mean it increase the lipid level in the blood. The first thing, measure turbidity, and we just we can just say that is logic, because if the lipid, because they are scattering the light, it's not absorb the light like a bilirubin, no, it is scatter the light. So the lipemia measured by turbidity. Turbidity is how the particles scatter the light, so they are scattering the light. Chylomicrons and the very low density lipoproteins are the largest lipoproteins, so they are increasing the turbidity. So what we understanding from this sentence, and increasing the volume of these lipids, in increasing the turbidity. So there are a proportional relationship between the size of the lipoproteins and the turbidity. So again, lipemia measured by the turbidity. Turbidity is the measure how these lipids scatter the light. Chylomicrons and very low density lipoproteins, I don't know, it's called chylomicrons, very low density proteins, and despite all these things, they are the largest lipoproteins, and they are increase the turbidity. To avoid the postprandial lipemia, blood is obtained after fasting. Like, so for example, like a glucose level. We want to measure the glucose level. We tell the patient, please fast before we want to take your glucose level, because we want to measure it accurately and we want to avoid the postprandial lipemia. Now we talk about what are the mechanism of interference of the lipemia. Actually, we have four mechanisms. Again, spectrophotometric, we have the volume depletion, we have also the electrophoresis and immunological, you will see it here, and the partition or partitioning of the sample. So we will understand it more. What is the mechanism of the lipemia? So the first one is spectrophotometric interference. How that is can be happen? We know that the lipemia measured by turbidity. So the absorptions of the light, it's about between 300 to the 700 nanometers. It's ultraviolet and visible light at this range. Many lipoproteins absorb the light, so between 300 and 700. Okay, you remember the NADH and NAD positive? So the NADH, NAD positive, the absorption of the light, it will be at the 340 nanometers. What that's mean? That's mean it in the same range level of the lipids. So the absorptions of the light of the NADH, NAD positive, is 340, but the absorption of the lipids, it's between 300 and 700, so that is will lead to the interference. And maybe if they are large molecules, they are scatter the light, so we can just this specific analyte that absorb the light, they cannot absorb the light, so that is lead to the false results. So we have two mechanisms why the lipemia causes interference or spectrophotometric interference. Now we go to something is called volume depletion or caused by the volume depletion effect. If there is an healthy individual and fasting, so that is lead to decrease 10% of the level lipids, so that is good for testing. But if healthy individual and postprandial, so that is increase the lipids more 10%, so that is lead to decrease the concentration of the specific analyte that I want to measure it, and that is lead to the false results. So the other thing that the volume depletion thing, and we can explain it like healthy individual and fasting decrease the lipid by 10%, while or decrease the level is less than 10%, but then the individual postprandial increase the lipid more than 10%, so that is lead to decrease the concentrations of the measured analyte. The other specific things is partitioning of the sample. How is the partitioning of the sample affect that? So we do something is called centrifugation. What we mean exactly by the centrifugation? Do you know what is mean exactly by the centrifugation? Centrifugation, to be optimal, just we collect the sample and wait 30 minutes for it, and then we put it into the centrifugation 15 minutes at the 5000 rpm inside the centrifugation. What is the centrifugation like? Separating the sample depends on the density. Okay, now we understand what is the centrifugation. And there is another question that has come to my mind, incubation, because we said in the DH5 alpha also the incubated under the ice. What is the incubation? Incubation means keep cells in a controlled environment. I mean, I control the temperature, I control the humidity, and control the oxygen. That's mean about the incubation. Forget about the incubation, focus on the centrifugation. Okay, so the other examples is partitioning of the sample. So we need centrifugation to test analyte, and we do the centrifugation, and imagine there is a lipid also. So the lipid by layer, it will be above, okay, and that is affect the absorbance or scattering the light. How that is can be happen? Let's understand how that is can be happen. So it's called partitioning of the sample. What that's mean, partitioning of the sample, like we making a separations of samples. Imagine if we want to measure analyte that it has like a lipid, and then it goes to the above, it go with the lipid. Then these lipids like scattering the light or avoiding the absorption of the light, so I can measure the analyte. Or imagine the analyte precipitate under, so also I can measure the light because they are scattering the light. So partitioning of the sample, if it contains lipemia, increase the lipid bilayer by the centrifugation, which is separating the blood contents according to the density, and then the lipid layer will be above Okay, so that is will scatter the light, and I can measure the specific analyte that I want to measure it. Okay, so spectrophotometric, and then volume depletion, partitioning of the sample. The other thing is psychochemical mechanism, sorry, physicochemical mechanism, like electrophoresis, like immunoassay. And we know that the electrophoresis is separating the proteins according to their molecular level, but also that maybe these lipids affected because it sometimes contains the lipoproteins, so electrophoresis and also immunoassay affected. It's again, what are the mechanism of interfering factors of lipemia or interfering mechanism of lipemia. The first one is spectrophotometric interfering, and also volume depletion, partition of the sample, and physicochemical mechanism like electrophoresis and immunoassay. About the blood, spectrophotometric, chemical, and also the components will be released outside and the dilution of the sample. The other questions is removal of the lipids. So we have two mechanisms of removal of these lipids, because just focus on me. We talk on the hemolysis. Okay, we talk about the hemolysis, and we talk how to avoid then the hemolysis happened to my sample. How I solve it? We said dilute the sample, but not always work, but dilute the sample. It's a good thing to solve the problem of the hemolysis. How to solve the problem of the lipid? Like this, I do the sample, and then all the lipid bilayer it's going above. Okay, but so what I can do, the first one is ultracentrifugation. Ultracentrifugation, I use high speed of the centrifugation, and that is leading to making all the lipid is above, then I remove it. Yeah, this is one technique. The other technique, we can remove it by the lipid clearing agent. Okay, and this lipid clearing agent, one of these example is called poloxamir 407. Do you hear about these things? We'll talk more information about these lipid clearing agents, but I want you just to focus how to remove the lipid. So we have two mechanisms: removal the lipid by ultracentrifugation, and removing the lipid also by lipid clearing substance. Ultracentrifugation, now we understand the centrifugation. First, collect the sample 30 minutes, then put it into centrifugation for 15 minutes, but that is not, like ideal things that we do to all the sample, but this is the best thing at the 5000 rpm. Okay, and the centrifugation is separating of these samples according to the density. Removal by the lipid clearing substance, one of these example is poloxamir 407. So there are multiple sources. I just searching what is a poloxamir 407 or 407. Many sources that said it's a synthetic. Okay, it's a synthetic that is happened by a human, or that is made by the human. Okay, it's a synthetic, it's a water soluble polymer. They are said water soluble, but in the most sources it has amphitic, amphitic, because it contains hydrophilic and hydrophobic parts. The hydrophobic, it's inside of it, in the center of it, and the hydrophilic, it's outside. So it has two things. Okay, it composed of the polyethylene oxidase and polypropylene oxidase. And the most important thing about the poloxamir 407, that at the high temperature it will be in a gel, in the low temperature it will be liquid. And imagine what the scientific thing that we use for it, poloxamir 407, when it's in the high temperature it will be gel, and the low temperature it will be liquid. You know that it's used in the drug delivery system. It used as excipient. You know what is an excipient? Excipient is in the inactive part of the capsule or the tablet or a drug. Okay, so good. And it's an important for the drug delivery. It acts as emulsifier. That's mean we mix it for the oil, so it's important for the separating of it. The other thing is important, it's not toxic. That's why we use it in the drugs. It's used also as lipid clearing agents because of the amphitic nature of it, because it contains hydrophilic, hydrophobic, and I said again, hydrophobic, it's inside of it, and hydrophilic it's outside, so that is easily dissolve and disperse within the water, so it acts as a surfactant agent. Okay. um, so again, I said polyximar 407 itself in a high temperature it will be as a gel. Okay, and it's a clearing substance. um, uh, Sometimes they hydrophilic non-ionic, but it's all the information said one thing, that is composed of the central hydrophobic block of polypropanelyl glycerol, and then found a block of the two hydrophilic blocks of polyethylene glycerol. So polyethylene glycerol, this is the hydrophilic part, and it has many application for that. It uses for cosmetics, it uses also for the contact lenses, it uses also because it removes the lipid films from the lenses, and also it used also in the mouth washes, it used also in the thermogenic properties. So all these are the uses of polyxyamir 407, and its exhibit, I said that it is approved by the FDA. It's in active integrated database. What else? It's used in the 3D biometering, and again, and I think that is the most important information, that is gel at the maybe room temperature, high temperature, and it's at the 40 Celsius. That's mean low temperature it will be liquid. Okay, so that is what is it about the polyxemer 407. Many information about it, so we have idea about it, but the most important thing that is an important as the lipid clearing substance. That's the most important thing, and we have to know the limits, like emulsifying the lipids in the sample. Again, emulsifying the lipids in the sample. The limits of polyxamir 407 that is maybe affect the concentration of the other analyte. Should validation that the polyxamir 407 not interact with the others, so that's maybe affect the concentrations of others. The other thing that is maybe take long time, which delay the results in critical clinical settings. So again, we back to our topic that we are talking about the polyxamir 407, or we can say 407 as we like, as a lipid clearing substance. Like we use it to solve our problem. We give the sample, and the sample is full of the lipid, and we have to use polyxamir 407 to reduce or to clear all of these lipids. But the problem, we have two problems about the polyxamir 407. That's unlikely or unexpectedly that is maybe interact with the other substances in the sample. This is the first problem. The other problem that is take long time to make its action, so that is not good in critical clinical settings. That's our thing about the polyxamir 407. Then we go back to our topic that we talk about the pre-analytic errors. The first one, hemolysis, was the most important pre-analytic error. Then we're talking about the lipemia, and then we go to another thing which is called icterus. So icterus, I mean increase the bilirubin level. The normal level it will be decreased, or maybe it's less or equal to 20 nanomole per liter. Again, micromole per liter, sorry, not nano, micromole per liter. So it should be less or equal to the 20 micromole per liter. This is the normal level of the bilirubin. If it's more than 34 micromole per liter, then it will be make a color change of the sample. I mean here of the sample. But if it's more than 100 micromole per liter, then it's make icterus. I mean icterus, like a patient that is have a yellowish discolorations of his sclera, of his skin, whatever is it. So again, these are the levels of bilirubin. The bilirubin level, it will less than the normal level, less than or equal to 20 micromole per liter. But if it's above 34 micromole per liter, then it's a color change of the sample. If it's clinically identified the icterus, that's mean more than 100 micromole per liter. Now we go to the mechanism of the interference of the actors. We have two: spectrophotometric interference and also chemical interference. Spectrophotometric, the bilirubin absorbance, it's between 400 till 540 nanometers. So any analyte in this criteria or this range, that will be interfere by the presence of the bilirubin, which is results by the hemolysis. So this is spectrophotometric interference, not absorbance, as I said. Spectrophotometric interference, because the absorptions of the light by the bilirubin, it's between 400 to 540 nanometers. How the chemical interference? Okay, this is a big topic also. Chemical interference, it interference with the measurements of the glucose, cholesterol, uric acid, triglyceride. But the question is why? Because the metabolism that is lead to the production of H2O2, and instead of binding of the H2O2 with the peroxidase, for example, and then it produce a colored compound, then we can measure, for example, the glucose level or a triglyceride or uric acid or whatever, then it binds to the bilirubin. So it's high affinity of H2O2 to bind to bilirubin, to bind to the bilirubin more than the peroxidase. Okay, you want to know, or do you want to understand it more? So that is lead to decrease the level of the analyte. So we didn't see any color around. Okay, this analyte is not a presence, but actually it's a presence, for example. So we have the glucose, then by the glucose oxidase, then it's formed gluconic acid and H2O2. Then the H2O2 that is bind to the peroxidase, and then it's formed the colored compound. Okay, so we measure the colored compound. It shows us how the glucose level that is a presence in our sample. But if there is a bilirubin, then it's bind to the H2O2 and then is leaded to the non-colored compound, and then it's not seen in the spectrophotometric. So that is explained why the actor is making a chemical interference with the glucose, uric acid, triglyceride, and also cholesterol. For example, like a glucose with the glucose oxidase, that is lead to gluconic acid and H2O2 and peroxidase, that is lead to the color compound, but in the presence of the bilirubin, H2O2 bind to the bilirubin, and that is lead to the non-colored compound. And that is lead to the false measurements of the specific analyte, like a glucose, triglyceride, uric acid, and cholesterol. So as a summarize, to remember everything, pre-analytic error, we have a hemolysis, lipemia, and icterus. What is the solution for them? Hemolysis by dilution, lipemia by fasting, icterus by dilution also. So we have something is called HIL indices: H hemolysis, I icterus, L lipemia. These indices are used to estimate the certain blood components. So when they said what these indices used to estimate the blood components. Again, H hemoglobin or hemolysis, I icterus, and lipemia. So what are the components that we measure it? H hemoglobin, fetal hemoglobin, for example. I icterus, so we measure the bilirubin, and we measure the turbidity. Okay, so I'm talking about the absorbance level, and then the reports should be the units. Hemoglobin, it will be gram per liter. Triglyceride, it will be millimole per liter. Bilirubin, it will be micromole per liter. We have to remember that very well. Okay, so again, what is the definition of HIL indices? These indices used to estimate the blood components. What is the blood components? H hemoglobin, I bilirubin, L turbidity, because we measure the lipid. Yeah, H hemolysis, how we can measure it? By the hemoglobin, but we said that is not a good estimate. I bilirubin, L the turbidity, because the lipid causes turbidity. Absorbance level, so we have many absorbance for the hemoglobin, but I will take this 540 to the 580. 540 to the 580. Bilirubin, we said before, that is from 400 to the 540. And the lipid, it will be from 300 to the 700. Okay, the units of these: hemoglobin gram per deciliter, triglyceride millimole per liter, bilirubin micromole per liter. And then we talking about the influencing factor, the interference factor. And we said the interference factor, these molecules, exogenous molecules that is already present on the sample, or we added to the sample, or biological constituent that is already present in the sample. And influencing factors, we subdivided them to the two types, in vivo and vitro, and we said most of them in the vivo. Okay, now we talk about the reference limits. The reference limits, actually they are subdivided into two types: subject-based reference limits and population-based reference limits. When I said subject-based reference limits, like it's all about these subjects. Like we have the healthy lab results of these subjects, and then, or today it's a patient, so there are another lab test for him, and then I just compare it with his lab healthy results. That's exactly what I mean by the subject-based reference levels. But the population-based reference levels, I take a group from this population, I have the results of them, and I make them as a reference. That's exactly the population-based reference levels. So the reference levels here, it's like this. Okay, like subdivided into subject-based reference levels, population-based reference levels. So we have the reference intervals, we have reference limits, we have a clinical decision limits, and I make table to understand what is the difference between them. We have reference intervals, so what is reference intervals, and what are the reference limits, and what, we just be confusing because they are look similar to each other. Reference intervals, range of values for healthy population to compare patient results with the healthy one based on the healthy adults, established by each lab, validated by the accuracy. Okay, then reference limits, range of the values showing the variation in a population to understand how the values differ among the healthy individual based on a specific reference individuals, requires understanding the population. Then the clinical decision levels, specific values to guide a clinical decision to determine that treatment may include a threshold for a specific condition and determined by the clinical guidelines. And there is something is called diagnosis threshold. Okay, now you feel that is confusing. Yeah, I know that. So I will just make a special note to understand what's it. Reference intervals, they are just values for the healthy individual, and if the patient come to me, I just compare it to these healthy individual, to these results from these healthy individuals. Okay, and just I said if it's patient or healthy one. The reference limits, it may be this patient, for me it's a healthy. Okay, and I just compare it maybe to the healthy results from the groups, and then I discovered that it's patient. The reference limit, it shows how these normal healthy levels, they are different among the individuals. Each individual has number. Okay, and we subdivided it into the subject-based reference levels limits and the population-based reference limits, just show how the normal levels are variations among the individuals. And then the clinical decision limits, it's easy one. That's mean we make a threshold. It's like a line, a short line between the healthy and the patient, and that is just to make us, this patient is sick and we have to deal with him now. It's important for a critical condition, it's important for clinical decisions. And here we make, for example, the glucose level. The normal glucose level is 70 to the 100 milligram deciliter. We can say just most of the healthy individual, they show us they are healthy when the range of the glucose is between 70 to the 100 milligram per deciliter. Then when I just make or show some variations among the individual, I discovered that they are from 60 to the 100 milligram per deciliter. And then the clinical decision limit, that's mean when it's above 126 or equals to it, that's mean this person is diabetes and I have to give him his treatment and make the control and these decisions. Okay, so now we understand what is the difference between the reference interval, reference limits, and also the clinical decision limit. These things we can't say what is it because you didn't see the above thing is selecting strategies for reference individuals. Like what are the strategies that I use it, or there's a different strategies that I can use it for their reference individuals. That's these individuals I want to use them as a reference. Okay, so what are the strategies that is can I use it? Maybe direct, indirect, pure, posterior, or we can use random and non-random. These are the many strategies that we use it for the reference individual. So the first one I will just what we mean exactly by direct or indirect. Direct, like collecting the samples directly from the person based on a specific criteria. Okay, and indirect, it uses existing data taken before. This is one strategy. Like, okay, I have a person and I wanted to know if it's healthy or patient. I just take the sample from him. Okay, collect the sample directly from him because it has like specific criteria on him, and just collect it directly from this person. But indirect, like, okay, in the both cases I collecting the sample from him, but the direct I just collect from this person before the same sample and just making comparing. Okay, but indirect I use the existing data. I don't have to make any sample, I just use existing data. Okay, so direct collect the sample directly from the person. Indirect, that's mean uses the existing data. This is one strategy. Other strategy, period, posterior. What gives mean exactly period? Period, that mean select the person, okay, before testing based on a criteria. Like I have a criteria and then select the person and then make the sample because I want to know new sample, new analysis, these things. But posterior, like behind, like I have this database and depending on this data I have to identify the person. So analysis previously collected data. So again, period, that's mean it's something before. Period or posterior to the patient. I take the person, okay? I choose the person, then collect the sample. Okay, I want a person that is patient, is told kaza, that's mean his age, like this, okay? And then collecting the sample from the person. So I have a criteria on the person, not on the sample. But the posterior, I have a criteria on the sample, not in the person. So I have data on this sample and then I researching for this person. The other thing is random and non-random. Random, that's me selecting whatever is it, and there is no bias in this. Okay, it's unbiased because everyone has the same chance. But non-random, that's mean I choose this person individually, and not they are not equally chance, so the bias it will be happen. So these are the different strategies of collecting the interference or reference individuals, maybe direct or indirect, period or posterior, or random or non-random. When you're choosing the reference sample for testing, balance between the practical needs and the potential bias. Even the non-random selection introduce bias, it actually reduce the bias. Blood donors, for example, regulate regular blood donate, so that is increase the iron level. Outdoor workers, so that is increase the vitamin D. Hospital staff, they are not on yeah, they are not healthy individuals on bedingti. What I can say, that's mean not all the hospital staff should be healthy. We talk about the reference limits. Now we're talking about something else. It's called interpercentile interval. That's mean I'm talking about the average. I'm talking the values that is present in the middle. I'm not talking about the biggest or the smallest. I'm talking about the values that is present in the middle. So we have something is called percentile. That's mean the value should be subdivided into 100 pieces, and I have to do the percentile for them, and it's subdivided into the parametric, non-parametric. The first one is parametric. It's actually for the normal distribution. So the sample size, it will be 40 person per group. It requires a Caucasian and a normal distribution. It's more complex. It needs requirements because I needed it for the normal population, because the interval or interpercentile interval needs to subdivide it into two groups, parametric or non-parametric. The parametric need to be normal evaluation, normal people. Okay, so it requires 40 persons per group. It needs normal Caucasian. It's more complex because it needs requirements for it. But non-parametric, at large size, 140 per group, no requirements, no expertise, because we want just to new discovering, because we need any distribution, because just we want to new discovering, as I said. So parametric, we need a normal distribution. Non-parametric, we do it when the distribution is unknown or skewed or something, and supported by the International Federal of Clinical Chemistry or Clinical and Lab Standards Institute. Now we talk about the hematocrit, and what is else about the hematocrit, that is a percentage, how much of the blood volume is occupied by the RBCs. Like there is a sample like here, and by the centrifugation there will be RBCs at the bottom, and then this a buffy coat of the WBCs and the platelet, and then there is a plasma. Just we measure the RBCs, like we measure the height of the RBCs divided by all length of the sample, multiply 100. That's exactly the hematocrit. So how much of the blood volume occupied by the RBCs? We can measure it by like multiplying of RBCs, the number of the RBCs, multiply MCV, multiply of 10. So these are the two calculations of the hematocrit. We can say the hematocrit is the height of the RBCs divided by the height of the whole blood sample, multiply 100. So we can say it's a percentage. Or hematocrit is mean carboxylic, or we can see cell volume, multiply RBCs, multiply 10. The hematocrit describes many things. Packed cell volume, or the volume of the packed cell RBCs, is the same actually. Erythrocyte volume fraction. There is something is called the erythrocyte volume fraction. Okay, so erythrocyte volume fraction. What should I do, or should I say also about it? I think it's enough for something is called hematocrit. Okay, and it's not talking about here the plasma, but we have to know that the plasma composed of the H2O plasma proteins, it composed of the O2 electrolytes, also that like a sodium, potassium chloride, and other things. And we know that the plasma protein subdivided into albumin and the globulin, and the globulin subdivided into alpha, beta, and gamma. The gamma are antibodies. We will discuss all this later, but we have to know that the hematocrit, we have two calculations. We can say height of the packed RBCs divided by the height of the blood sample, multiply 100. Hematocrit, it can be RBCs, multiply MCV, multiply 10. Now we talk about the antithrombin 3, and from its name, antithrombin, so preventing the clotting because it's acting on the coagulation factor, especially two factors, 2 and 10. So the other name for it is called serine protease inhibitor. So we have antithrombin 3 or serine protease inhibitor. heparin enhance the activity of antithrombin 3. And in the bottom I see the small amount of heparin activate 1000-fold of antithrombin 3, so that is lead to the rapid anticoagulation. Again, and what is the action of the antithrombin 3? It's inhibit the activity of activated coagulation factor 2 and 10. Okay, and it's not reduced likely to the DVT. Yes, if it's reduced antithrombin 3, so that is leading to easy to happen the clotting factors that is lead to the DVT and VTE. Again, because that's so important, antithrombin from its name, that is a prevent the coagulation. But the question is prevent the coagulation, but which mechanism? If it's preventing the clotting factor or preventing the platelet accumulation or aggregations. Actually, the antithrombin 3, it's preventing the coagulation factor. It's not any coagulation factor. The preventing the action of activated coagulation factor, factor 2 and factor 10. 2 and 10. The other important thing that the heparin activate the action of antithrombin 3. So even a small amount of the heparin that lead to the activation of the antithrombin 3 by 1000-fold. Imagine that. Now we go to other thing, and there is another name, serine protease inhibitor. Now we talk about the kaolin. So what is a kaolin? Kaolin, sometimes they just coated this tube with the kaolin or just added it to the serum. And remember, I said serum and not plasma, because one thing, because the plasma, okay, no coagulation, there is no clots in the plasma, but the serum there will be clots factor. Actually we needed it to for reclotting, so the kaolin is increasing the clotting in the serum. How it's increase the kaolin in the clotting in the factor? Because it's activate the intrinsic pathway. That's mean activate the factor 12, which is called Hakiman factor, I think, and then that it will lead to an increased activity of factor 9, factor 11, sorry, and then factor 11 activate the factor 9, and factor 9 activate the factor 8, 9 and 8 activate the factor 10. So this is the intrinsic pathway. Okay, so kaolin, it activate the intrinsic pathway. So again, activate the factor 12, which is called Hageman factor, and 12 activate factor 11, 11 activate factor 9, 9 and 8 activate factor 10. Deal. Now understand that. So kaolin, it measured to use APTT, which is measure the intrinsic coagulations pathway. So the question is, how is the kaolin activate the intrinsic pathway? Why is the kaolin activate the coagulation pathway? And the answer is because it causes as a negative charge inside the tube or on the surface of the tube, and that what is mean, that is lead to the activate the clotting factor. Still understand it? No. Why the negative charge activate the clotting factors? Why that? Because we just imagine what is happening in the nature. Okay, the kaolin actually is estimate the tissue injury. So when there is a tissue injury, that is lead to the expose of the extracellular matrix, and after the exposing of the extracellular matrix like DNA, RNA, ribosomes, protein, other things, most of them they contain the negative charge, and this negative charge activate these platelet coagulation factors and the intrinsic pathway, and that is lead to the activation of a clot. So what is happen is the kaolin simulate the tissue injury by creating a negative charge on the surface of a tube. So the sample, it just imagine that there is a tissue injury while there is not. and then the clotting happen, and then that is activation the intrinsic pathway, so we can measure the ABTT. So now we understand why is the kaolin used in the serum sample. Now we go to other thing is EDTA and citrate. Remember that EDT and citrate, they are anticoagulant. So we know, like we just said many things, that they are anticoagulant, antithrombotic anticoagulant, citrate anticoagulant, EDTA also anticoagulant. The only one that is coagulant is kaolin. Okay, remember that. So we have the citrate, and also we have another thing which is non-EDTA. Both of them act as anticoagulant, okay? But what is the difference? That the citrate is reversible, while the EDTA is irreversible. Both of them bind to the calcium, but the citrate not to preserve the cell morphology. EDTA preserve the cell morphology. Citrate, it has short time to avoid the changes in the activity of coagulation, like short action. But EDTA is stored for a long time because it's irreversible, you know. But here, short time, it should be happen in a short time to avoid the changes in the activity of coagulation factors, because it may be like reverse action, okay? And then when we use it, EDTA, because I don't want to the coagulation anymore. So I use CBC, I use a blood smear, I use a skeletal test, I use it also on the flow cystometry, because I don't want to see any coagulation in the sample. So I use irreversible anticoagulations like EDTA, and at the same time it preserves the cell morphology. It takes a long time, so it's ideal for me. But if I wanted it to just measure the coagulation and how many times that it will be happen, so I use citrate because it's reversible, take short time, and then go to the action like this. So PT, ABTT, TT, and also finding fibrin level in the platelet function test. So everything that is associated with the platelet. So we have here EDTA and the citrate. The common things between them, that they are binding to the calcium ion, so they have the same mechanism. But EDTA, it's irreversible anticoagulants, preserve the cell morphology, take a long time because it's irreversible. It's used in the CBC, blood smear, flow cystometry, and also to skeletal disease, because I don't want any coagulation that happened in this time. But in the citrate, I use it as a reversible anticoagulant. It also binds to the calcium, not to preserve the cell morphology. It's short because it's reversible, and used is to measure PT, TT, ABTT, and also finding the fibrin and the other thing, that platelet function test. All that is associated with the coagulation. So again, antithrombin, citrate, EDTA, all actions are anticoagulant except the kaolin. Okay, kaolin, that is increasing the coagulation. That's exactly why we use in the serum sample. So that it will be the last part of our lecture today. Hope you understand anything. Goodbye.